So in the last lecture, we discussed about the key properties of the dynamical systems and the physical significance of the state. Uh, we also discussed about the zero state response of the linear system, both in the time invariant and time varying case. Again, both in the continuous time domain and the discrete time domain. Third, we discussed the particularly for the LTI system, we discussed its solution in the frequency domain because we saw that if we want to compute the response in the time domain, that then you need to compute the integral and the convolution. So we use Laplace transform as a tool to compute the response in the frequency domain first, and then by taking the Laplace inverse, we computed its solution in the time domain. We also saw the relation of the zero state response with the state space representation of the system. The major issue where we stopped in the last lecture is the solution of the time invariant time varying system. So there were two issues to compute the solution of the time varying system, that the Laplace transform of the function gt comma tau would now be a function of two variables, and also the major issue is this point, the second point, where the Laplace transform of the multiplication of the time varying matrix A of t into the vector xt is not equal to their individual Laplace transforms. So today we will see the solution of the linear time varying systems in the time domain, and then we would tailor it or tailor the solution for the time invariant case. So first we'll start with the homogeneous LTV systems. So we start by considering the solution to a continuous time. So this abbreviation is used for continuous time, linear time varying system with a given initial condition but zero input. So we are not supplying any input to the system. If we recall the initial representation of the state space, it was x dot is equal to a of t xt plus b of t u of t. So now we are taking that u of t is equal to 0. So similarly this whole part would go to 0, and we are dealing only with this homogeneous part. And the initial condition at time t is equal to t naught is denoted by x naught, which is also again an n-dimensional vector for all t, and we are computing the solution for all t greater than or equal to 0, or in fact it should be equal to t naught. You should treat this as t naught, because if t naught is equal to 0, then we have the initial condition at t is equal to 0 other than time t naught. So there is a very nice property associated with the homogeneous system, that when we compute the solution, the map from the initial condition x t naught is equal to x naught to the solution xt at a given time is always linear, meaning to say that we can individually study the response of the state space system by first considering the homogeneous equation and then by considering the non-homogeneous equation because of the linearity property. Now we here introduce one theorem which also gives us the solution of the equation 4, or the homogeneous LTV state space equation. The unique solution to 4 is given by x of t is equal to phi t comma t naught into x naught, where x naught is the initial condition and this response is valid for t greater than equal to 0, where phi t comma t naught is basically computed by this non-ending series which we call the Peano-Baker series. This n cross n matrix phi t comma t naught is called the state transition matrix. Now here you would see, since A is a time varying matrix, we are having the integrals of this state matrix, which is the A matrix, as the non-ending series. Now let's see further the properties of the state transition matrix, because if you pay close attention to this series, it is quite complicated to compute all these integrals, and we never know that how much integrals we need to compute. So first we will see the properties, that what are the properties or key properties of the state transition matrix. and then we will try to compute the closed form solution of this state transition matrix. So the first property speaks that for every t naught greater than equal to 0, phi t comma t naught is the unique solution to this equation. This is a very nice property which we would explore later. And phi t comma t naught also satisfy is equal to I. I here is an identity matrix. Just to add in the last slide that here I denotes the identity matrix of the suitable dimension. Now if the state transition matrix is a matrix of dimension n cross n, then this I is an identity matrix of containing 1 in its diagonal of dimension n cross n. Okay. So similarly here I is a n dimensional identity matrix for t greater than equal to 0. Second, for every t, s and tau greater than equal to 0, the state transition matrix satisfy this property, what we also call the semi-group property. Now see, let's say this is the some straight trajectory, and on the x-axis we have, which is the time axis. Now given this initial condition x naught at t is equal to tau, and I want to compute the solution at t is equal to s1, which we denote by x1. So this solution, owing to the previous theorem, is given by the multiplication of the state transition matrix, which says that I want to compute the solution at t is equal to s, given the solution at t is equal to tau, and the initial condition at t is equal to tau is x0. Okay. Now if I want to compute the solution, let's say at time t, then my x2 I can represent in two ways. If I know x0, then I can represent by the multiplication of the state transition matrix phi at time t, given the initial condition at tau multiplied by x0. Okay. Or if my initial condition is x1, because I know that this solution would be a unique solution. So in that case, the state transition matrix would be computed by the response at t, given the initial condition at s, multiplied by that initial condition at t is equal to s. So I could write x2 is equal to phi t comma tau x0, or phi t comma s is equal to x1. Now if I put x1 from here to here, it would give me phi t comma s into phi s comma tau is equal to phi t comma tau. Okay. Now the third property speaks that for every t and tau greater than equal to 0, we have phi t comma tau is non-singular, that is the state transition matrix is non-singular, and this relationship is always satisfied. That phi, if we take the inverse of the state transition matrix, then the order of the argument would change. So if we pay attention to this phi, it says that we are seeing the response at time t, given the initial condition at tau. Now if I take the inverse of this state transition matrix, it gives me phi tau comma t, meaning to say that I am now taking the response at t is equal to capital tau, given the initial condition at time t. Okay, you can change the order. We would see the relevance of this property when we will discuss about the discrete time solution of the time varying case. So the important part here is how to compute the state transition matrix. So first of all, let's consider again the homogeneous system by x dot is equal to a of t into x. So we know then for every initial state xi of t naught, which is an n dimensional vector. Now here I am taking different initial conditions. Okay, so for example, if I say, okay, let's suppose, forget about this, let's say we have x, this original x is equal to x1 and x2. Okay, now this xi of t naught says that I have an n dimensional vector which I call, let's say, x1 of t naught, which is again an n dimensional vector at time t naught. Okay, if I have x2 of t naught, meaning to say again it would be an n dimensional vector but for another values, right? So then for every initial conditions we could have different initial conditions, which would be an n dimensional vector. Then there exists a unique solution xi of t, which is also again an n dimensional vector for all i's starting from 1 to the dimension of the state, from 1 to n. Okay, now as the first step, arrange all these n solutions as capital X, which is equal to all these n dimensional vector arranged in columns. So this would yield a square matrix of dimension n cross n, because every vector x of x1, x2 up to xn, they are all n dimensional. Okay, because every xi satisfy 5, this is what we have computed. We can write x capital X dot is equal to a into capital X, right? If we are, so we can see, for example, let's say just consider the case of only two initial conditions. Okay, so this I could write a of t, this would be a derivative, then x2. So in the preliminary step we have computed that x dot 1 is equal to a of t x1, and this 1 in the superscript denotes the different initial condition, but the state would remain the same. Basically this is equation number 5. So if I club all these equations 5 for different initial conditions having a different unique solution, then it would give me this equation, right? Now if x of t naught is non-singular, meaning to say that if I club all these x at initial conditions is non-singular, or we say that these n initial states are linearly independent, then x of t is called a fundamental matrix of phi. Basically the fundamental matrix of phi. Now here two question arises: whether my x of t is unique, and second is x of t non-singular for all t. Now the uniqueness property is straightforward. Why? We will come on to these questions later on, but first we will see one simple example which demonstrate the computation of this fundamental matrix. Let's say we have this homogeneous equation where this is the A matrix. Okay, now I can write these complete state equation into two differential equation, that is x1 dot is equal to 0 because the first row is equal to 0, and x2 dot is equal to t into x1. So we can see in detail. Let's say like this x1 and x2. So this says that x1 dot is equal to 0 and x2 dot is equal to basically t into x1, right? Now we can compute the solution of this equation, and the solution of this equation is x1 of t is equal to x1 of 0, and this is only driven by the initial conditions. Okay. Now if I put this x1 of t into the second differential equation for the second state, I would get x2 dot is equal to 2x tx1, which is finally equal to t into x1 of 0. Now I can compute the direct integral because it is quite simple integral, and finally I would have this solution. So I can compute the solution of x1 and I can compute the solution of x2. Now we choose two different initial conditions. Let's say one initial condition is 1 0 and another initial condition is 1 2. Now these two initial conditions should be linearly independent because of the property we saw in the last slide, that if these two initial conditions are linearly independent, then that matrix would be a fundamental matrix, right? We could quickly verify in the sense that if I multiply alpha 1 of into x1 of 0 plus alpha 2 x2 0 equal to 0, then alpha 1 and alpha 2 should be 0 for the linearly independence, right? Then and that only this equation can be satisfied. So if I compute the solution for these two different initial condition, we get one solution this and another solution is this one. Now if I club both these solution into one, which would give me this x of t. This is the fundamental matrix. So this is how you can compute the fundamental matrix. Now we see, now to answer these two questions, so we can take the first one about the uniqueness. We know that there could be infinitely number of initial conditions, and we know for every initial condition there would be a unique solution. So x of t is basically not unique. For different initial condition we would have different solution, and if the initial conditions are linearly independent, then x of t being the fundamental matrix would not be unique, right? About the singularity, we will see this result in the next result, which say let x of t be a fundamental matrix of x dot is equal to AT into x. Then the state transition matrix is given by the multiplication of the fundamental matrix and the inverse of the fundamental matrix at time t is equal to t naught. Okay. Now because xt is non-singular, for all t its inverse is well defined. Let's see. So this is the example. In the last example we computed the x of t. If I compute this x of t at t is equal to t naught and multiply by this matrix with the inverse of the fundamental matrix at t is equal to t naught, I would get this state transition matrix. So instead of computing the Peano-Baker series, we can compute the closed form solution of the state transition matrix in terms of the fundamental matrix. Okay. So once we computed this phi t comma t naught, you can verify by yourself all the three properties which we had discussed initially, that the solution of the state transition matrix, the semi-group property, and also the non-singularity and the inverse property. Okay. Now see we can go back to the original non-homogeneous LTV system where now we have included the U as well. Okay. The rest of the thing remains the same, that we have the initial condition at t is equal to t naught, which is given by x naught. Now in this result we also call this the variation of constants. The unique solution to 6 to this system is given by x of t is equal to the state transition matrix multiplied by the initial condition plus the integral from the initial time to the current time multiplied by the state transition matrix, the input matrix, and the input signal itself. Okay. Now if I put this x of t back into this equation, because the second equation is basically the algebraic equation. So second equation says y of t is equal to c of t multiplied by whole this equation x of t plus dt ut. Okay. So we know that phi is the state transition matrix. Right. So there are certain properties of this result, that the equation 7, basically this equation is called the variation of constants formula, by which it gets its name, variation of constants. Okay. Now this is the overall response of the y of t. And in the last lecture we saw that the total response is basically driven by two individual responses. One is the zero state response and another by the zero input response. So here if we put the u of t is equal to 0, then both this part will go away, and the solution we would have only this one which we saw in the last result also. So we call either by the zero input response or the homogeneous response. Now if we have the initial state x naught is equal to 0, then the only response is this one because of the input signal, and we call it either the zero state response or the forced response, which is given by this part. So if you see some similarity from the previous lecture, basically in the last lecture we discussed only this response. Okay, we will see that what is the relationship between the impulse response and the state space representation of the time varying system. Okay, so here we will, because this is an important result, we will go through very quickly the proof of proof of this result, that whether this x of t and y of t is a solution of this LTV system. So we just recall the previous equation because we would going to use these three equations into the proof. So there are two parts of the proof. First, that this part x of t should satisfy the initial condition. The second part is this one, meaning to say that because this is the x of t, now in this equation 7, if I compute at t is equal to t naught, the solution should be x of t naught is equal to x naught, right? Now let's put t is equal to t naught into this equation. So it would give me x of t naught, which is equal to phi t naught comma t naught, and from the property of the state transition matrix, phi t comma t is basically equal to the identity matrix. Okay, so the x naught would remain. Now if I put t is equal to t naught here, this integral would vanish, right? So the solution we would have that x of t naught is equal to x naught. Now the second part of the proof, I need to put xt into this state space equation. So I need to take the derivative of this 7. Let's we take the derivative. X dot is equal to, because this is the only part which is a function of time, so we take d phi by dt into x naught, plus by using the differentiation rule of integral, because inside the integral we have only the function phi, which is a function of t. So we take the derivative of this function phi. B and u would remain as it is, we won't be taking the integral, plus the final value of this integral at time t. So tau basically would become t, phi t comma t. All the taus would become t, right? So we would have phi t comma t bt into u. Okay, u basically is u of t, because we are computing the solution at time t is equal to t. Now we can replace this part d phi by dt by using the property that which is given by d phi by dt is basically the solution of a phi t comma t naught. This was the first property of the state transition matrix. So if we put this here, we get this, that at phi t comma t naught into x naught. Phi t comma t is basically the identity matrix, so it would go away, and bt ut plus similarly we could replace here as well, and then this part would remain. Okay, now if we take a of t common from this term and this term, okay, we would have phi t comma t naught x naught plus this part, and basically this is the solution x of t. right? So we could replace this whole term by xt. So we have x dot is equal to at into xt plus bt into ut, which is this one. So when we put this solution into the left hand side of this equation, it becomes equal to the right hand side, meaning to say that this equation or this solution satisfied this equation plus it satisfies the initial condition as well. Okay, and simply if I put this x of t here in the right hand side, it would become equal to the left hand side. Okay, so we can say that this xt and ut is basically the solution of this linear time varying system. So this is straightforward, that 8 is obtained by direct substitution of xt in y of t. Okay, now let's see some interesting facts about the solution, because in the last lecture we studied the impulse response. Now here we would try to relate the impulse response with the state space representation of the time varying system. So we saw in the one of the previous result that the zero state response is given by this part. Okay, the zero state response. Now I can write this last part by this equation, meaning to say, because this part dt into et was outside the integral. Now to take this inside the integral, what I did, I multiplied by an impulse function. So I know that at t is equal to tau, this would be equal to this one. Okay, so we so I can write the zero state response by taking this part inside the integral, inside the integral. Okay, and which is equivalent to the gt comma tau into u tau. Basically I can replace this whole part by gt comma tau. Okay, and this is the impulse response. So this is the relation between the impulse response of the time varying system and the state space solution.